I'd really like to begin by putting out a bit of a theoretical framework around why water matters. The work which I do really puts water within a systems perspective. I look across infrastructure sectors and adaptation to climate change very broadly. And so we're really interested in how water fits within that systems perspective. And then I'll give two more technically based snapshots, one from Britain and one from the Eastern Nile. I'm using the branding of the FCDO funded REACH research program, which is a big research program in Oxford. There's actually a number of other pieces of funded research which I'm going to touch upon. I won't bother acknowledging all of the different funders, quite a lot of funding from UKRI in here as well. This is a cast of 1,000, so I can't acknowledge all of my co-authors either, but I'll put a slide with some references at the end, so you can look down the other names there to see all of the other people who've made massive contributions to this work. To begin with, a little bit of conceptual framing, and this comes from a large report which I co-chaired with Claudia Sadov, now at CGIAR, and David Gray, visiting professor in Oxford, formerly World Bank, who many of you will know. A few years back, we co-chaired a study for the Global Water Partnership and the OECD called Securing Water, Sustaining Growth. And we were really trying to position the relationship between water and national goals of growth, wealth, well-being. We observed how countries have different water endowments, and water can represent both a destructive threat to national goals and a productive opportunity. And the threat comes through familiar water-related risks, water-related disease, harmful water quality, floods, droughts, which represent a drag on growth and on people's well-being. And we did quite a bit of analysis of this. It's analysis which has also been subject to a fair bit of critique as well. We like that in academia. We've been criticized for being reductionist, for being geographical determinists. I certainly challenge the reductionist framing because we very much think in systems terms. And we do that so that we can think about, well, what investments in water security, which might contribute to those productive benefits, investments in information, in institutions, in infrastructure, and then what are the protective actions we can do to manage those risks, which represent a drag on the development goals that we're aiming for. And incidentally, in here, there's another feedback in that small arrow that's just appeared, is that we need to recognize that as countries develop, they actually increasing their exposure to these water-related risks. They're developing in floodplains, they're using more water resources, and that is increasing their exposure to droughts. And so there's a potential actual build-up of risk, which, for example, the celebrated American geographer Gilbert White identified back in the 1950s. And within this GWP study, we have made some very kind of tentative hypotheses around the trajectories of these water-related risks. We know that thanks to a huge amount of international action, the MDGs and then the SDGs, the risks from inadequate water supply and sanitation are gradually going down, whilst the risks from climate-related hazards are going up. And partly that's to do with climate change, but mostly it's to do with this increasing exposure of populations. And then again, just a hypothesis here, but we're certainly seeing increasing ecosystem degradation and pollution. The reason we hope there will be some tipping of the curve here is that we see that as countries transition into becoming middle income, they begin to pay more attention, often too late, unfortunately, to the chronic effects of pollution and ecosystem degradation. So that just sets some kind of framing for why and how we think about water-related risks and their relationship to development. How do we operationalize that? Well, following on from this, I did with colleagues in the World Bank some work to develop a dashboard. We wanted to pretty much bring together almost all of the facts you would need in order to diagnose water security in one page. The arrows represent the trends, so we're doing time series analysis as well. And so in a sense, that connects you back to the previous slide where we are saying, well, what are the trends of these different water-related risks? And you can see that we're looking at, in the left-hand panel, at contextual drivers, what's going on with population, the economy, the climate. The upper right-hand panel is all of the facts about the water resource system, and I'll come to this in a moment. How much renewable water is there? What unconventional water is there? What's the water being used for? So who's it being allocated to? How does agriculture compare to industry and so on? What's the state of the infrastructure and the water institutions? And then in the red and the green panels, we're beginning to look at impacts and the actual outcomes. What are the observed outcomes for people in the environment in relation to water-related risks? Let's just dive in a little bit more. I refer to this water system, and I think that that's very central to how one then goes about operationalizing these concepts. This picture will be familiar to you, but I think it helps to get your head around the way in which water is being withdrawn, managed, treated or not, and then used for municipal, agricultural, industrial purposes and returned or not to the environment. And that kind of framing then goes about, well, how do we actually model these things? And there have been massive advances, both in terms of our capacity to model climate and variability through downscaled climate modeling, weather generators, stream flow generators, and so on, groundwater. Then at the center of this, and I think sometimes too often overlooked, is what's actually being done with water. Once it's withdrawn, where is it stored? Where is it piped to? Who's using it? And how reliable are their uses? And that relates to how the water resource system is actually being managed. What are the abstraction rules? What are the reservoir operation rules? And so on. And with this type of modelling system, this is an example from the Thames in Britain, in fact, we pay a lot of attention to validating it as well. So the panel at the top is reservoir levels in the lower Thames reservoirs. And we want to make sure that these package of system simulations represents reasonably well what's actually going on in the system, because that's important for what we want to find out, which is we use this package to analyze how risks are going to change in the future. And so the vertical axis here, it's a little bit technical, but it's basically an annual probability of severe water shortages under a range of different exogenous drivers. Here we're looking at population growth, and without any additional adaptation, though we're also, and one thing which is very significant in Britain at the moment is ratcheting up, quite rightly, of environmental flow requirements, which means that abstraction licenses are being scaled down in many places. But we recognize that there's a trade-off here. If you do that and you don't do anything else, then the probability of water shortages for people and industry is going to go up. And then we use the same type of analysis set up to begin to analyze the adaptation options. And within this one, we've got the black line is the no options, which you've just seen. But then we can see, well, how much could be achieved with demand management and leakage reductions. And at some point, you probably need a large new supply side intervention as well. Here we're looking at a 150 megalitres per day reuse plant, which would bring another dollop in on the supply side. And the way in which we think about that is that this is another kind of dashboard representation, but this is through time, where we can in the top panel project the climate ticking down slightly in terms of the summer flow. but then an exposure indicator that is driving upwards. This is population, which we're expecting to go up at least through until the middle of the century. So that's driving up the demand. And then in the middle panel here, there's a combination of adaptation interventions, efficiency technologies, leakage reduction, metering, but then sometime towards the middle of the century, the need for a large supply side intervention. And in the bottom panel, we're showing how those various factors all add up to give changing risk. And as you go into the future, more uncertainty on that changing risk. So we're plotting out what the future might hold with respect to water security. In Britain, there's been a lot of focus recently, given that the south and east of the country, there's practically no more water in the environment which can be licensed. So there's a lot of look at effluent reuse, and we already have desalination, and at interbasin transfers. So my team have been working on this for a long time now, developing the modeling capability to look at a national scale. We drive that with a large event set of synthetic droughts from bias-corrected climate models. If you're looking at this big scale, you have to get the spatial variability properly. What really matters for a transfer is if you have a drought in one basin, are you also going to have a drought in the neighboring basin where the water is coming from? So we've done a lot of work on the joint probability of that problem, and then developed this national model, which at a fairly aggregate scale looks at the entire water resource system of England and Wales, and that's being used by Ofwat and the Environment Agency at the moment to look at all of these transfer schemes. And the types of results we get from that are those probabilities of severe shortages. This is baseline, near future, far future. The more the shortages are, the horizontal axis here is the duration of restriction. And this is a real kind of resilience metric here. How do you cope? How long does it take you to start recovering? And how is that changing in the future? And this type of simulation modeling enables you to look at that as well. These, again, are baseline scenarios. The next thing you do is, well, what are the adaptation interventions which can bring these risks to a manageable level, to bring them back down in the graph, and to improve resilience, so to shift them leftwards so that the restrictions are not as long and we're recovering faster. So then finally, in slipping kind of seamlessly, and I think this is kind of quite neatly seamless, if you don't mind me saying, to Africa, where with my colleague Kevin Wheeler, and also with a number of other colleagues, in particular Dale Whittington, we've been working on the impacts of the Grand Ethiopian Renaissance Dam on the Eastern Nile for many years now. And this has just got hotter and hotter in political and diplomatic terms as we've been working on it, and particularly using this type of simulation modeling. In fact, another modeling system called Riverware, which Kevin's very central to look at the impact of the GERD on downstream water resources, in particular in Egypt at the Aswan High Dam. This is a very long story. Kevin shared me 80 slides, and it was absolutely fascinating. Went right the way back to Hirst's role in the hydrology of the Nile in the 19th century. There are some kind of really interesting headline stories from this. One is that because Lake Nasser is relatively full at the moment, as the GERD fills, it will have an impact. And if they fill it very aggressively and there is a bad climate variability outcome, there may be shortages, but the probability of very critical levels is actually very low. But it would be much better if there was an agreement on a compromise on how the GERD was filled. And once the GERD is full, under normal hydrological conditions, this is a hydropower reservoir, so the water will flow through, and the High Aswan Dam reservoir will operate a bit lower and it will be less variable, but it doesn't look like it will be a threat to Egyptian water releases downstream from Aswan. The critical thing in this whole story is a hugely complicated piece of hydrology and geopolitics and engineering, is if, and it's not a question of if, when there is a severe and multi-year drought on the Nile. Having the GERD there actually will buffer the effect of that drought at the start, the onset, so you can see before the green line, the black solid line is actually above the dotted line, which is before the GERD, because there'll be continued releases from the GERD downstream, which will buffer the drought. The critical thing is what happens at the end of the drought. To optimize their hydropower, the Ethiopians would want to fill up the GERD as quickly as they can, but that would prolong the drought down in Egypt, and that would be seen as being a deliberate action. You can't blame that on hydrological variability. The existence of a drought, of course, is hydrological variability, but how you do the refilling is a decision. And it's how that decision plays out that they need to agree upon. That was a quick diversion into a very interesting story, as well as hopefully providing you a bit of information about that extremely important part of the world. It gives you some sense of the ways in which both thinking in terms of risk and using systems analysis enable us to tease out some of the issues and trade-offs associated with how water-related risks are manifesting themselves. And I hope I've illustrated that by analysing and modelling these systems with a real focus on risks, on outcomes for people and the environment, we can explore future scenarios, we can see how effective they are at managing the future and understand how risks might evolve for many different actors as well. One of the things we've been criticized for is that we don't recognize distributional issues. That is absolutely wrong. And the attraction here is that we can look at how risks are distributed to different actors, both at a very aggregate scale, like between Ethiopia and Egypt, but also at a more micro scale, like between different communities and different economic sectors, between agriculture and industry, for example. And we can use that information to identify, implement adaptation pathways that are designed to equitably manage those water-related risks. And I'll close there and just put a few papers up there, mostly to acknowledge the many other people I've worked with on this, and also in case you want to follow up on any of this.